technical difficulties in this. I'll try to keep it brief, though. So let's begin with the prayer. This is Aquinas' prayer before study. In the name of the Father, and the Son, and the Holy Spirit. Amen. O ineffable Creator, who from the treasures of your wisdom have established three hierarchies of angels, have arrayed them in marvelous order above the fiery heavens, and have marshaled the regions of the universe with such artful skill. You are proclaimed the true font of light and wisdom, and the primal origin raised high beyond all things. Pour forth a ray of your brightness into the darkened places of my mind, disperse from my soul the twofold darkness into which I was born, sin and ignorance. You make eloquent the tongues of infants, refine my speech, and pour forth upon my lips the goodness of your blessing. Grant to me keenness of mind, capacity to remember, skill in learning, subtlety to interpret, and eloquence in speech. May you guide the beginning of my work, direct its progress, and bring it to completion. You who are true God and true man, who live and reign, world without end. Amen. In the name of the Father, and the Son, and the Holy Spirit. Amen. All right. So the topic of today's talk is, why is the sky blue? Which might seem like an odd question to ask, but just indulge me for this first little bit of it, and put your mind in my head when I vision this, and this might be a cultural thing. At least in the United States, this is one of those like vague questions that like a child will ask their parents. And the parent gets worried because they don't actually know the answer. And so they usually try to make something up quickly that sort of makes sense. If you've ever read the Calvin and Hobbes cartoons, I'm imagining Calvin asking his dad something and dad making something up. So imagine that you have a child asking his parent, why is the sky blue? And the parent doing their best to respond, and yet constantly getting asked again, well, why? Well, why? That's the first part of what we're going to go through. And I claim this will lead us into a Thomistic philosophy of nature, but we'll see how successful that is. So why is the sky blue? Just take for a minute, like, what would your answer be? Why is the sky blue? Maybe you studied this, maybe you haven't, but the first answer, well, because the sun is out. I mean, it might seem like an obvious answer, but at night, the sky isn't blue. The sky is blackish, maybe a little bit purplish, depending on where you are. Depending if you're far enough away, there might be this myriad of colors of the Milky Way, but the sky isn't always blue. The sky is only blue when the sun is shining on it. So that's, I mean, obvious in one sense, but not unimportant. You can't completely ignore that fact. So an explanation the dad could give his son is, well, because the sun is out. Now, the chances that would satisfy this little child are pretty limited. So, but I know that, but why? Why is when the sun is out, is the sky blue? It's like, well, because the sky is a bunch of gas. It's a big atmosphere. I mean, it might not be obvious, but I mean, when the sky is out on the moon, or when the sun is out on the moon, the sky is black. There is no gas. And so despite the fact that the sun is up, it looks just like pitch black night. I think you can't see as many stars perhaps, but it's pretty much black. So there's something about the fact that there is this layer of gas that is the sky, the thing that we're able to breathe and is so important for our ecosystem. So that's a hugely important part of this. But again, the chances of this satisfying our precocious child are fairly limited. So he pushes on. Well, why? Why is it that you know this gas looks blue? It's like, well, okay, maybe Dad's had read a little bit of physics here and there. Well, because right, so it's transparent, like the light flows through it, but in certain points, right, the air absorbs a little bit of the sunlight, and it reflects back toward us, right? It's not as if the only light coming to us comes directly from the sun. There's light that, you know, when we're not looking directly at the sun, which you should never do because that would hurt yourself, you're looking at other parts of the sky. That light from the sun hits the air is excited in some fashion, and then that light is now sent back towards us. So we see light, we see a brightness coming from all of the sky. So something about this transparent atmosphere seems to absorb some bit of the sunlight, but because it can't just hold on that energy, it sends the excess towards us. So we see the brightness of the sun all over the place. That's why, again, on the moon, you only see light coming directly from the sun. Everywhere else it's black, whereas when you have this atmosphere of gas, it's coming from all directions. Okay, but still, like, you haven't answered the core question. Where does the blue come from? Why is the sky blue? All right, now we got to get serious. Okay, so this atmosphere of gas is made of molecules, of various gases, which it turns out we've discovered to be much smaller in size than the wavelength of light. So the place where that light is absorbed and the direction it is re-emitted is completely random. If the sizes were closer in scale, there might be a directionality to the way this works. There's other factors, but because the molecules are so much smaller than the wavelength of light, they get spread in all direction. And we've discovered that the amount of light that is refracted or absorbed and re-emitted depends upon the wavelength of light. So while there's lots of wavelengths of light coming from the sun, the blue side of it, the shorter length wavelength light, is much more likely to be scattered towards us. So while in theory, light of every color is scattering towards us, the blue is the most common, and so that's what we see. So maybe, just maybe, that might be enough to satisfy our precocious child, but it's very likely he could just keep asking why, and we could keep giving more because answers, right? Okay, well, why is so why is it that this light is this whole range of wavelengths? Why is there any blue light coming to us at all from the sun? Well, because the light of the sun is a mixture of various light wavelengths. The surface of the sun actually has a black body source of a particular temperature. The interior, why is that? Because the interior of the sun is optically opaque, and so it's just the surface that is emitting on most of this light. Why is this? Because the interior of the sun is undergoing nuclear fusion. Why is it that we get blue light in particular, but not even shorter wavelengths of ultraviolet light? Well, because the human eye is only sensitive to a certain range of light. Why is it? Because ultraviolet light will interfere with important chemical reactions, be bad for us. Okay, well, why is it that the light is bouncing off of the molecules at all? Well, because light is an oscillating electromagnetic field with a particular wavelength. Because electromagnetic field will push charged objects around, so there's charged objects in those atoms that are oscillating and re-emitting things. Because the gas molecules have distinct positive and negative charges in the nuclei and the electrons. Because moving charged objects cause changes in these electromagnetic fields. So as these charged objects are moving, they themselves create electromagnetic fields that are sent off the light. Okay, I'm going too quickly. So I'm not expecting you to absorb all of this, but the point is you can keep asking these why questions, and there's more things to it. Some of them move backwards in time. Okay, there's light hitting the atmosphere. Where did that light come from? Some of it digs more deeply into the nature of that interaction between light and these molecules. Some of it might be about, well, where did the gas that is the atmosphere come from at all? And look at the history of the Earth and the origin of the atmosphere. There are tons and tons of why is it this way? Why does it act this way kinds of questions that we could ask, and tons of because kinds of answers that we could give. Now, roughly speaking, all of these becauses that I've been putting out are, at least in some sense, scientific. Some of them might seem fairly simplistic, like, okay, the sun is out. How scientific is that? Well, it just is a fact that we can observe the sun being up and not. You can get into the whole notion of the orbit of the sun. There's a scientific grounding to even that simplistic fact. But they draw on different aspects or features of what the sky is and its relationship to the environment around it. The sun in particular, in us in a lesser way. Some of these answers draw in particular on what is happening to the sky, the fact that the sky, this atmosphere, is being bombarded by a bunch of photons. Some of them draw more on the shape or the structure of the sky. If the atmosphere were much more diffuse or thinner, then it wouldn't look exactly the same way. The fact that it is a gas of a particular character that takes up a certain amount of space has a big portion to do with the particular way the sky looks to us. Some of them draw more on how the sky, this collection of molecules, tends to react to things. What is it that the light that isn't bombarding it tends to do, and how does the sky tend to react? Some of it draws particularly on the stuff the sky is made of, right? The particular molecules that go into the complex collection of gases that is the sky. Some of these answers blur the edges, where there seems to be a mix of a couple of these or pairs of them. What I would argue is that what we're diving into in this seemingly silly, seemingly simplistic discussion, sort of scientific discussion of the sky, is that we're asking the sort of questions that lead to what Aristotle thought of as causes. For Aristotle, a cause is not just the way we often think about causes in a contemporary conversation, where a cause is a thing that pushes or acts on something else. That is a part of the Aristotelian understanding of causes, but in part because of linguistically that link between the word for why and the word for because in Greek and Latin. Cause was a much broader idea for Aristotle. in general, a cause was any sort of answer to that question, why? Why does something exist in the way that it does, act in the way that it does? Why is it the sort of thing that it is? In the natural order, we can know that a particular substance or particular type of thing exists, that it acts or reacts in certain ways, that it undergoes some changes. But for every fact that we know, we can ask why and give various answers. So I'll go back to this guy, but just in my training as a natural philosopher, the squirrel is one of the most common examples brought up. So I feel like I had to incorporate the squirrel into this very briefly. Like when we think about a squirrel, why does a squirrel exist? Well, because it had squirrel parents. There were, it came to be from some other squirrels. Why does a squirrel exist? Well, because it is a concrete living being of a particular type of species, the Thomistic hudoniscus. This is I think the North American brown squirrel. So Hudson has the Hudson Valley. So the squirrels here might be different. But it's not a dog, it's not a cat, it's not a plant, it's a particular kind of thing. But it's also, it exists. Why does the squirrel exist? Because it's the sort of thing that wants to eat and grow and procreate. That it doesn't make sense to understand a squirrel fully just as this thing sitting here, but understanding it as the sort of thing that strives to run away from predators, to seek out food, to seek out a mate and procreate. And why does the squirrel exist? Because it just is a particular stable homeostatic collection of organs and cells and molecules that maintain itself as a squirrel and somehow prevents it from just diffusing into other, those particles and things that make it up, diffusing into something else. This, for those of you who are familiar, is in some ways leaning into Aristotle's instinct that there were, broadly speaking, 4 general types of answers to that question, why, particularly when we're thinking about the natural world. 4 general ways in which we might try to answer that question. And in a certain sense, and importantly, these 4 ways of answering the question why are not independent of one another. That to fully understand something, you need to, in a certain sense, address all of those aspects. So simply saying the sun is out is not a complete answer for why the sky is blue. You need more than that. Simply saying the squirrel had squirrel parents is not a complete answer for understanding why the squirrel exists. If you don't have that, in a certain sense, something is lacking in your understanding of the squirrel, but it's not complete. And so classically, these 4 types of causes were split, the 4 that Aristotle laid out became known as the material cause, the formal cause, the efficient or agent cause, and the final cause. The material cause is, broadly speaking, that out of which something comes to be and which persists, the matter or stuff that it is made of. Again, there's a lot more depth of conversation to be had about what we mean by that. The formal cause is the form or the archetype, the statement of the essence. And this is, again, a very vague notion just in that one sentence from Aristotle's Physics Book 2. But as you dig into it, it's about, yes, something of maybe the shape and the organization of a thing, but also its various powers and activities. The efficient or agent cause would be the primary source of a particular change or coming to rest. So if we're asking for the efficient cause of some change, we're looking for that thing that is the primary agent, the primary external cause of that particular change or coming to rest. And the final cause is the end, or that for the sake of which a thing is done. So these 4 have come to be known in the kind of Aristotelian and Thomistic tradition as the 4 causes. And in a certain sense, we can, I've been implicitly including this in the way I've been talking about our question about why the sky is blue. Right? If we think about why the sky is blue in terms of the fact that, okay, the sky is not always blue. Sometimes it is dark. So there's a change that happens to make the sky blue when the sun comes up. And to fully understand that change, at least a first step in this would be to make sure that we've covered all 4 of those causes. That we understand that the sky is made up of this particular mixture of gases, that it has a structure that is this sort of envelope of air that sits around the earth, that in this that is giving off this blue light when the sun is shining on it, that the light from the sun is the thing that is exciting the air and causing it to glow with this sort of blue hue. And that this excited air, that this change of the air in a certain sense is not permanent, but a tendency of this air to absorb and release energy, and a tendency to do it particularly for light that has the lower wavelength, sort of the blue spectrum, rather than other spectrums. We could also ask, I mean, it's important, to recognize that Aristotle kind of bounces back and forth between talking about the four causes in the context of a particular change. We can also ask about the four causes of a particular substance, a particular thing. But I think for the sake of time, I'm going to move on from that. There's a whole lot more that could be followed up with that conversation about change, getting into questions of chains of causes of different forms, change of a chain of efficient causes. So, the photon is hitting the light, the photon is being sent, is being emitted by the sun, but that energy of the sun is coming from the nuclear reaction going on in the center of the sun. There's a chain of efficient causes leading back to that. You could arguably talk about a sort of chain of material causes going down, talking about the sun is being, or the atmosphere is being made of these molecules. Well, the molecules are made up of atoms, and those atoms are made up of protons and neutrons. Those protons are made up of quarks. You can move all the way down in that direction. So there's more to be said about any one of the causes, and so in one sense, the investigation of why the sky is blue is not completed by simply listing off one thing for each of the causes, and yet the causes are an important tool for helping us to recognize, have we really addressed all the different important aspects of what goes into this thing, as I would argue. Now, instead, I'm going to go in a different direction and propose two possible objections someone might have made to the sort of silly exercise I was doing. One is, okay, you're a special pleading argument that, okay, you're just choosing to organize your explanation of why the sky is blue to fit the four causes. You knew they were out there and you were just like, how could I force this into it? Okay, well, here is the first Google search result for why the sky is blue that comes up from McGill University. Their little like science discussion. And there's a little paragraph here. The sky is blue due to the phenomenon called Rayleigh scattering. The scattering refers to the scattering of electromagnetic radiation, of which light is a form by particles of much smaller wavelength. Sunlight is scattered by the particles of the atmosphere, and what comes through down to the earth is called diffuse sky radiation. And though only about a third of the light is scattered, the smallest wavelengths of light tend to scatter easier. These shorter wavelengths correspond to blue hues, therefore, hence why when we look at the sky, we see it blue, et cetera, et cetera. I don't see the word cause in there anywhere. Four causes, nowhere to be seen. I would argue that if you actually think carefully about any good scientific explanation, you will almost certainly find an echo of the four causes in it. So if we look at this, right, in a certain sense, it's not explicitly stated, but the fact is they're implicitly bringing in different aspects of this organization of thinking about how something works. Just the word sunlight, in a certain sense, implies necessarily, okay, this is when the sunlight is actually interacting with the air. If the sun weren't there, if at night, this wouldn't be happening. So that's, in a certain sense, an implicit reference to some sort of efficient causality. And it's scattered by the particles of the atmosphere. There's an implicit reference to what the atmosphere is made of, that there are particular molecular and atomic particles of various gases. And the very fact that we say atmosphere, it seems like it's such a common word, we don't think of it having a lot of weight behind it, but that implies this array of gas that is this envelope around the Earth. And if a child were reading this, they might need to look up the definition of the atmosphere, and they would learn about the general structure of gases that surround the Earth as the sky. And in some sense, maybe the final cause might seem to be the hardest, but in some way, as we'll say a little bit more later, if we think about final causes in the highest way, as if it were the way we think about our final causes, human efforts and striving and desire, where we think through and intend things, then you're very likely to find any intention. I would argue you would find no conscious intention in why the sky is blue. But that's not the fundamental sense in which Aristotle and Aquinas think about final causality. That is a part of final causality, but in real sense, only the highest part of final causality. There's a way in which the most basic form of final causality is simply the fact that stuff tends to do stuff, that things have a particular nature and tend to act in a certain way when interacting with particular kinds of things. that might seem simplistic, and in a certain sense, it is, because we take it for granted. Because we have lived in a particular scientific culture for so long, we just take for granted the fact that nature is orderly and tends to act in certain ways as a bare principle that we don't even need to think about. But this need not be obvious. And in fact, Aristotle, in certain ways, was arguing against thinkers who were skeptical of that natural tendency of things to act in certain ways, and more open to a much more chaotic and random view of nature. So even just this little phrase, the smallest wavelength of light tend to scatter easier, is at least a hint towards this notion of final causality, that there is a way in which light tends to act when interacting with air. If there were no standard tendency, then it wouldn't dominantly be the blue hue that's refracted. It might be just randomly distributed across all of them, and so it might come to us more as white light. Or it could be some arbitrary God deciding that this day it's going to be red, the next day it's going to be green. In one sense, that sounds silly to us, and yet there's no philosophical reason why that couldn't be the way the universe is. The sort of regularity and order of nature implicitly implies something of a very bare and weak sense of final causality. Okay, so that's my sort of attempt at an initial response against that first objection of special cleaving. In a certain sense, yes, when I first wrote this out, I was trying to find the four causes in this particular explanation. But I would argue that any good scientific explanation, the four causes are almost certainly, at least in echo, present in the depths of that conversation. A second objection that might be raised is, okay, well, look, you're just dealing with like the popular account of how to talk about, popular science account of how to deal with the fact of the sky being blue. The real scientific answer is in the equations. It's in the fundamental physics that describes the interaction of light and matter. So simply talking about an envelope of gas and tending towards blue, that's not scientific enough. We need to get into the math and the details of it. So if you're talking about that, the sky is blue because of the standard model of particle physics, or whatever theory will actually complete it that happens to be true. Right. So there's some fundamental theory of physics that we're working towards and maybe don't have yet. And once we have that, that will be the why, the explanation for everything that happens in nature. Now, there's a sense in which that is compelling, and a sense in which that is true, but a sense in which that is incomplete. So I want to respond to this objection in two ways. Once, in a certain sense, just taking it on its face value and saying that even here in the standard model of particle physics, you find the four causes. And then I want to talk about a second response saying that even this hope or this claim that we can explain everything in nature simply by deriving it from first principles of particle physics, one, we haven't done it yet, and two, there's a good chance we probably can't do it, and why that is. So first, just to get a sense of what the standard model of particle physics here, this is sort of a very cheap attempt to explain what's going on. So you have over here, you have the collection of particles that exist in the standard model, the particular ways that energy can exist in various fields. Again, we talk about them generally as fields. They manifest as particles in certain ways. I don't want to get into that for now. I'm going to just generally talk about them as fields. So there are these there's these sort of 17 general ways that matter can manifest itself in fields, or energy can manifest itself in fields. And then there's this whole long list of instructions for how these various fields can translate into one another. How if I have two fields, if I have if I have energy of these two kinds of fields near each other, they might interact in such a way to produce a different field and sort of add to the energy in a different field. Or the way in which a particular field will interact with itself as that energy is spread around in that field. And so this is where things like the mass of the particles come in, the strength of the interaction. And so we have a list of stuff and instructions for how that stuff interacts, right? So I would argue that already here, we're already talking about matter and form, right? We're talking about energy in some way that can be distributed in space and time only in these various fields of the standard model. So again, I'm sort of presuming the standard model is complete. It's not actually, but it seems like any theory that would complete it would sort of follow along these lines. There is no energy, full stop, in the universe. There is only energy that manifests in particular forms, and existing in, at this level, existing in particular fields. In various other contexts, we might talk about things like kinetic energy and potential energy. Don't want to dive into that too much. But at this bare level of the standard model, there just is energy, but not energy never exists as just energy without any properties. It always exists as energy of a particular kind of field. And we define that field. It's a little hard to see, but there's these little numbers next to each of these particles. Those correspond to the quantum numbers, various charges. So electrical charge, the color charge for the strong force, the electroweak charge, the masses of the particles. And these are numbers that describe how these particles interact sort of with themselves, how the field interacts with itself, and how various fields interact with one another. So for instance, right, the electron, because it has a electrical charge, will interact very easily with the photon, which is the primary gauge boson for electric field, but it will never, ever, in any circumstance, interact directly with the gluon, because the gluon has no electric charge, but it does have a color charge. The electron has an electric charge, but no color charge. So those two fields will never interact. So there is a way in which the particular fields manifest certain activities. We can label them as having certain properties, and most of those properties deal with how those fields interact with sort of themselves in a certain sense and with other fields. So this is a formal aspect of what we're talking about, the form of these fields. Each field represents a particular possible manner that energy, matter, can actually exist with certain properties, quantum numbers, and certain powers that relate to those properties. In a more detailed way, the particular instructions for how these particles are going to interact has to do with that long list of equations I popped up. That gives you the details of exactly how these things link together. So at this point, I could go into an aside about how this is suspiciously like Aristotle's four elements in a way that sounds kind of silly. But just the bare point I want to make is, if you notice, there is no smallest unbreakable pieces of matter in this picture. Matter exists in various forms, but none of them are unbreakable. All of them can transform into other kinds of matter. There are no atoms in the Greek sense of unbreakable pieces, or even in the early classical, early modern classical physics sense of unbreakable atoms. That our understanding of material order is, in a certain sense, I would argue, fundamentally hieromorphic. There is some base stuff that we generally label energy. Energy is not exactly the same as prime matter for various reasons that I'm going to punt on for now. But there is some underlying stuff that manifests in different manners, but nothing that it actually exists in is completely unbreakable. All of them can transform into one another. Very, very much like Aristotle's understanding of the four elements as being the four fundamental ways that prime matter can exist in reality, but none of them being completely unbreakable and transforming into one another. Okay, so there's already a certain kind of Thomistic and Aristotelian understanding of the fundamental aspects of reality that we can start to see in the standard model of particle physics. As we move to the idea of efficient causality, sometimes people make the argument that, right, in quantum mechanics, we've lost all sense of efficient causality. It's completely random and chaotic, and there's no such thing as efficient causality anymore. But in actual fact, I mean, particularly when you're dealing with particle physics, right, you talk in languages of efficient causality all the time. So for instance, right, so this is a Feynman diagram. This is a fancy way of writing out one particular kind of interaction, and this funny little diagram translates into a fairly complicated equation based off of the rules that were present in that very long equation, the Lagrangian standard model. But basically what this is saying is, as we move from left to right, You start with an electron and a positron. They annihilate, become a photon. That photon then decays into an antiquark and a quark, and the antiquark spits off a gluon. There is a certain efficient causality here because we can say it is the electron-positron pair that did something, that annihilated to become this photon. In actual fact, this would probably be a virtual photon. Gonna punt on that. That would then create a quark-antiquark pair. And in this diagram, at least, it seems like we can say that it's specifically the antiquark that is the cause of this gluon coming out. Now, there's a certain sense in which, this is very much a simplification of a lot of what's going on, right? It's never actually this clean. In this particular example, for instance, these quarks having what we having a color charge, so being subject to the strong force. These are the things that make up protons and neutrons. That quarks and antiquarks never exist on their own for long. They combine into other particles. So if you actually looked for this in an experiment, what you wouldn't see two nice particles flying off. You'd see this massive, ugly jet of particles flying away that are this sort of recombined collection of quarks and gluons into most likely protons and neutrons and a few other maybe exotic forms of those. Secondly, right, this is just one Feynman diagram. For most processes, there's going to be lots of other Feynman diagrams that contribute to this. So this is a part of the story of what's physically going on, but only a part of the story. So there's a sense in which we don't necessarily have access to these kinds of details, particularly when we're doing an experiment, but there are very real senses in which we can talk about agency. The very fact that physicists say that they have discovered the Higgs boson, no one's ever actually seen the Higgs boson. What have they seen? They've seen that there is a certain kind of signal coming out of the Large Hadron Collider experiments, that signal could, in fact, and often is created by other kinds of particles that we know in the standard model. But it happens so frequently that it only makes sense to say there must have been a Higgs boson, like there must be something like the Higgs boson that adds to an excess. That means that there's this particular type of result, the particular collection of particles we end up seeing down the line must have been caused by a Higgs boson. For any one event, we may not be able to say that this one right here, I know for a fact that the Higgs boson was here and it caused this result. But when we step back and look at over time, it is absolutely true that there is a part of nature that has the properties of the Higgs boson that caused the overall statistical results that we have. With very strong confidence, we can talk about that causality, if not for one particular event, at least for the overall working of nature. So while efficient causality can get more difficult in quantum mechanics, it hasn't been eliminated altogether. What about final causality? For many people, this seems to be the hardest because in one sense, it was the one aspect of the scholastic tradition that the early modern scientists were almost like most strongly reacted against. It's a debate between whether they hated formal causality or whether they hated substantial form or final causality more. But that's either way. These are sort of like they're boogeymen in a lot of their, like if you read a lot of the early modern scientists, so Descartes and Newton, all of them are trying to claim they're not doing this and accusing one another of doing it so when they're trying to put down other people's theories. But a lot of that comes from this notion of final causality as high-level intentionality, as if it were an intellectual being that is choosing something to happen. And again, for Aristotle, it's not that. It's a much more low-level tendency. So there are various ways in which final causality shows up more explicitly or implicitly in particle physics, in these kinds of interactions. First, most of the particles in the standard model are individually on their own unstable. They're only going to exist for a period of time before they decay down to a more stable state. And they decay in extremely regular patterns. When they decay, exactly when they're going to decay is indeterminate in quantum mechanical, but what they're going to decay into is very, very standardized. There might be a couple of options, but we actually know the frequency with which the Higgs boson decays into this collection of particles versus that collection of particles, or a muon decays into this collection of particles versus that collection of particles. A muon never decays into a quark and a gluon, or a quark and a gluon. It would never happen. It would be impossible. So there are certain natural tendencies of how these unstable particles interact. Secondly, the very process by which we use the standard model of particle physics in quantum field theory in general, the most successful tools we use today, is a kind of a quantum mechanical version of what in classical mechanics is known as the principle of least action. I don't want to go into the detail here, but basically when we do a calculation, we presume some initial state and we guess some final state, and we try to figure out the chance of starting from that initial state and getting to that final state. There's a way in which we are actually predicting what we think is going to happen. In a certain sense, either knowing or guessing what's going to happen, and then figuring out exactly how nature would get us from point A to point B. This is a debated point among physicists about whether this is explicitly an introduction of final causality into nature. This started in the development of classical physics when the principle of least action was developed. But there are at least arguments that there is a tendency of nature to seek out certain pathways and not others. That to get from point A to point B, there are certain pathways that are more likely and less likely. This seems very vague, but in a certain sense, it is this very kind of reasoning that has given us the most powerful tools for thinking about all sorts of very, very common physical phenomenon that in one sense have been known for a long time, but completely understood. For instance, we couldn't actually give an explanation for why light refracts when it moves through glass until we started using quantum mechanics and this sort of method of principle of least action. We could predict what we saw what would happen. We could explain that it happened, but giving an explanation for why it happened required these sort of quantum mechanical thinking. More fundamentally, though, the third aspect of final causality, I'm going to quote St. Albert in a passage from his book on minerals. So he's talking about rocks and minerals and inanimate things. And when I first came across this quote, it was very confusing and striking, but I think it's actually an important fundamental principle for thinking about nature in a Thomistic context or an Aristotelian context, particularly when thinking about the inanimate. So in this book, he starts out by laying out the four causes of, he starts with rocks first, then goes to metals. And so he spends a whole chapter on efficient causality, talking about the heavenly spheres acting on things and the particular location stuff is at. He spends a whole chapter on material causality, like the way in which the four elements combine. He also includes sort of alchemical things like sulfur and quicksilver. He spends a whole chapter on the formal causality and the fact that metals and rocks have substantial forms and why we know that. And he has one sentence on final causality, this one right here. But we need not look for a final cause, for in physical things, the formal cause is the final cause. That sounds like a cop-out, and yet I think he's right. I think what he's trying to say here is, if you think about the squirrel comes to be as an embryonic being, right? That is a squirrel, but that's not a very good squirrel. It has potential to become a very, very good squirrel, but it's not there yet. It needs to grow and mature before it comes to be the fullness of what it is to be a squirrel. There is an interior teleology of the squirrel that directs it towards maturing to its perfect state and then staying there once it gets there. Think about the creation of a diamond. Does a diamond take time to mature into being a perfect diamond? No. Once the conditions are proper and the diamond properly takes on the form of diamond, it is a mature diamond. It has achieved that telos of what it is to be a perfect diamond, and it spends the rest of its existence trying to fight off things that are forcing it to become something else. So there's a certain sense in which once a material inanimate thing has achieved its final cause, or achieved a particular formal cause, it has achieved its end, its mature state, and the rest of its effort and activity, as you might want to talk about it, the rest of its teleology is about trying to keep that form and not be forced into some other. So the very pattern of action and reaction between fields that is describing the standard model is both the formal cause, but also when understood as the tendency of matter to try to stay in particular states, in certain stable states, these natural tendencies, it is the final cause as well. So even here, at a base level of fundamental particle physics, we find echoes of the four causes. And I think these can be made much more concrete and serious. So even if you punt to, well, let's just look at the best physics we have, that's where all the real explanations are. Good explanations coming out of those, I think I would argue, will still, if not rely, at least lean into the four causes as understood in a kind of Aristotelian Thomistic context. The second part of this response to the, well, let's just look at the particle physics, that's where all the real answers are, is in actual practice, no scientist has ever derived Rayleigh scattering or any other sort of macroscopic interaction of light with the atmosphere directly from the Lagrangian of standard model. I feel fairly confident to say that's true. I definitely haven't. Most physicists haven't. I don't think anyone has actually completely derived this phenomenon simply from the Lagrangian of standard model. Why is that? Because it's really hard. Most particle physics calculations, the sort of things that, I mean, they peter out at roughly 8 to 10 particles. You're really pushing it as you get into like 12 and 13. There are ways in which you can focus on the simplest particles to try and extend that out into the dozens, but it requires sort of presumptions and creativity. And even with like the best tools in mathematics, it's still a really hard problem to get 8 to 10 particles. This is like, thankfully, this was not what I was working on in graduate school because it would have killed me. But I had friends who were trying to do these sorts of calculations and do them at a very complex level. And it's very, very hard, right? So like 1 liter of gas has roughly 10 to the 24 particles in it. So you're not going to give a complete explanation of what's going on by simply, okay, let's plug in the initial state of the atmosphere into our Lagrangian and the collection of all the photons from the sun and just work it out. It's just not going to happen. It's at least calculationally hard. I would argue, I would be surprised if we could ever build a computer big enough to actually do that calculation. It's also not clear that even if we could, it's not 100% clear it would work. Why is that? So we can say certain things about, for instance, the interaction of light with electrons. That's actually like a soluble problem in quantum field theory. It's one of the like initial calculations you end up doing when you're learning how to do all this stuff with the standard model. And it's called Compton scattering. This is the basic interaction of photons with electrons. It's Compton scattering when you have a very high energy photon. It's Thomson scattering at low energies where we'd have sort of visible light. And importantly, for these low energy photons, a free electron will interact with and scatter light of any frequency at all equally. So what I mean by that is it doesn't matter how energetic the light is, it's going to interact with all of it. Or it's going to interact with it at the same rate. If you had a free electron not bound to any other particles. The closest we get to this, oh shoot, I meant to pull this up. The closest we get to this, and just for the sake of time, I'm going to kind of move through this quickly. The closest we get to this collection of free particles in a material sense is when we talk about plasmas. Plasmas are when you take a gas and excite it, and the electrons get stripped off of the atoms and are floating around freely for a little while as long as it's hot enough. It's like fire. If you've ever seen like a fluorescent light is a plasma. And one fascinating thing about plasmas is they are opaque. I mean, if they're very thin, you might be able to see through them, but they will interact with light of any frequency that comes through and absorb that light and send it back. So they give off light due to the interaction of the free electrons with the ions that are in there, but they are opaque to any exterior light coming through. And as the free electrons, they scatter any light that tries to come through that plasma. But electrons that are bound in atoms, if you let them cool off and reduce into neutral atomic structures, they become almost completely transparent. They end up only primarily interacting with light of very specific frequencies. So it's the same electrons, it's the same relationship between electrons and photons, but because now the electron is part of this neutral structure that is an atom, the nature of its interaction with light changes. so that instead of interacting with light of every visible frequency, it will now only interact with very specific visible frequencies, ones that correspond to sort of transitions to different states in the atom. Don't want to go down that line for now. But so that neutral gas, like our atmosphere, will be generally transparent. And so whereas if our atmosphere were a plasma, it would be completely opaque, right? We would also be dead for various reasons, but it would be completely opaque. So there's something about the basic interaction with matter that changes when we move from free particles to neutral atoms. So yeah, I'm going to skip ahead here. And importantly, like, as you see, like, it depends on what kind of atom you're in as to how exactly that electron is going to interact with matter. Same thing as it gets to more complicated molecules, the interaction changes. But you might say, okay, well, yes, but these particular properties of how each atom interacts with light can be arguably built up from quantum field theory, quantum mechanics, right? There's a whole field of quantum chemistry that tries to do this, that tries to use quantum mechanics to explain the details of various chemical interactions. So this is a soluble problem, right? We've done this. Chemistry, it's basically just physics, right? Not quite. I mean, it is an open question in quantum chemistry and in the philosophy of chemistry if these various properties, even just basic properties of the periodic table, can be completely reducible down to quantum mechanics and to quantum field theory. It hasn't been done yet, and some think that it can't simply be reduced to physics. Okay, well, look, this Rayleigh scattering, right? The scattering that allows the sky to be blue only makes sense if okay, so let's given that, fine, but at least if we think about the sky as being just a bunch of atoms, right? This only makes sense for this diffuse, mostly transparent gas, and the intensity of the effect will depend upon the density and temperature of the gas, but at least all of this stuff, right? This stuff that goes into the standard calculations on Rayleigh scattering, what is the index of refraction of a gas and the density of the gas, all of that has at least been reduced down to the motion of molecules, right? I mean, temperature, anybody's taken a basic chemistry class, temperature is just average kinetic energy, right? Not so fast, right? I mean, for instance, let's see, yeah. So right now, the air in this room is, broadly speaking, a particular temperature, and the air outside is a much, much higher temperature. And it's a good thing we're in here. If we open that door and stood in the middle between the outside and the inside, there's a very concrete sense in which the gas that is in that doorway doesn't have a temperature yet. There is an average kinetic energy. We could, in theory, like figure out the kinetic energy of, say we took, you know, the 1 meter width section of air that is in the doorway when it opens. There is an average kinetic energy, but that gas is this weird, complicated mixture of the gas flowing out from, you know, from this room and in from this room, and it is not in equilibrium yet. There's a way in which it is only when that gas is fully in equilibrium that the idea of temperature makes sense. But in a very concrete way, there is no microscopic explanation of what this equilibrium is without importing something of the idea of temperature. There's a way in which philosophers of chemistry, it's a debate amongst them about whether this is a soluble problem or whether it's a circular sort of thing, whether these macroscopic properties like temperature actually can be reduced simply to the collective activity of molecules. And temperature is like the easiest possible case. If you want to get into phase changes, freezing, melting, boiling, it gets much more complicated. Okay, so in a bit of summary, but why is the sky blue? I would argue that it still is the case that like the best explanation for why the sky is blue seems to be that the sky is an envelope of air, which is made of a mixture of gases, that when acted upon by sunlight, it tends to scatter light, especially blue. And that explanation leans into this fourfold structure of causes. Behind each of those statements is a host of chemistry and physics and mathematics, which deepens but does not ultimately eliminate this causal picture. And I'd argue that this is an exercise in the philosophy of nature. So what exactly is this philosophy of nature that I've been trying to lead us into? drawing on Father Philip Neri's definition, right? So it is the science of changeable being, insofar as this can be known through strictly material principles. And I would argue that those material principles include, but are not strictly limited to, the four causes. These are four of the fundamental principles that go into any good explanation, any good knowledge we can have of material nature. More generally, Thomistic natural philosophy in particular argues against certain ways of thinking about the material world that at various points in history have become more or less common. It argues against atomism, that there are some smallest unbreakable material pieces, against reductionism, that macroscopic phenomena are completely reduced down to the motion of their parts. And in a more indirect way, it argues against physicalism, that reality is completely explainable from material principles. And while not all would agree, I'd argue that modern science actually argues similarly, that a lot of these Thomistic instincts actually can be found in our best understanding of the material world. Now, this is not all that the philosophy of nature does, right? There are other principles in the philosophy of nature, some of which have been implicit in our conversation about act and potency. The very idea of matter and form is rooted in this notion of act and potency. I kind of dropped in the notion of potency and possibility at various points. Arguably, quantum indeterminacy has a whole lot to do with potency. It's a conversation for later. The idea of substances versus accidents. We've, in a certain sense, been focusing on a lot of different accidents, properties, the color, the activity of things. What substances have we been dealing with? Good question. This is an open argument among Thomists. Some would want to lean into the idea that the molecules being substance. I tend either towards the idea that there's something about air as a whole that's a substance, or maybe different substances mixed together. But that's a conversation for later. More broadly, this hylomorphism, this general notion that reality is physical reality is made up of substances that are a composite of prime matter and substantial form, with various accidental forms inhering in the composite. I hinted at the notion of prime matter at various points, less so substantial form, but this is kind of under the hood of the discussion we've been having. There are lots of other topics that are less directly involved in our discussion, questions around time and place, the infinite and the void, and even in a certain way, proofs for the existence of immaterial substances. In theory, you should be able to go from this question of why is the sky blue to the fact that there are immaterial substances. I haven't quite worked out all the details yet, but I think there are easier ways to make that argument. But in principle, anything in nature is a stepping stone towards that deeper conversation. So with that, I want to just leave you with a couple further readings. If you're interested in this sort of thing, here's a couple of, I think, helpful references for good introductions to the idea of philosophy of nature, particularly in the context of contemporary science. Yeah, I'll just leave it at that.